Okay, Benny, welcome back to the E3SM All Hands webinar. Our speaker today is Tian Zhou from Pacific Northwest National Lab, and Tian is working on hydrological modeling and is going to be presenting to us about river processes in E3SM. And Tian, go ahead.
Okay, thanks. Thanks, Susanna. For my name, today my talk is improving the representation of river processes in E3SM. Before my talk, I want to first acknowledge some of my our team member who have contributed a lot to this effort, including Ruby for advising and mentoring, Guoyong, Natalie, Hongyi, and Tony for the model development, and Teklu, Yuna for the data support. Outline of today's talk. I would like to use 2 slides to briefly review the river model in E3SM and some developments has been made in phase 1. Then I will introduce 2 ongoing studies related to the river process and the river model. Then I will use another 2 slides to introduce some ongoing developments and some future directions. First, some brief review for the river model in E3SM. As we know, E3SM has 7 components here in this plot. I'm gonna only focus in these 2 components, which is river and land. And by the way, I grabbed this figure from the website, and I think it's not been updated because this name is still ALM and CAM. So when E3SM started a few years ago, the original river model is a simple linear reservoir routing model called river transport model, RTM. And Hongyi actually replaced this simple river routing model by a more physical based MOSART. As you can see from this figure, can better represent the subgrid cell river network by including hill slope subnetwork and main channel river routing. It has a more physically based algorithm to represent the river flow dynamics using kinematic wave routing scheme. So this is a great platform for the future development. So in phase 1, we actually had 2 other development based on the MOSART. First is from the left side, you can see Natalie developed a water management model coupled with the MOSART. So the water management model actually can redistribute it can model the dam and reservoir operations in the river network, and it also allows you to assess the water demand at each grid cell and redistribute the irrigation water from the river channel and the reservoir to the cropland. Also, another development is done by Xiangyu, which is also based on the MOSART. What it does is that, as you can see, for each grid cell, it divides the channel cells into 2 parts. One, so it has a channel which constantly has water, and the inundation floodplain, it can communicate with channel, but it can represent the flow, the water coming in and out to represent the inundation dynamics between the Amazon basin. As you can see, so the top one is the simulated results presenting the flood inundation extent, and the lower one is the observation based on the satellite. So you can see it did a good job, but as I said, it's only being evaluated in Amazon basin. So the development is not only happened in in the river model part. In the land model, in ELM, we also have developments in terms of the irrigation scheme. Guoyong did publish a couple of papers, actually improved the irrigation schemes in ELM. So currently, the irrigation scheme is coupled with MOSART WM with a one-way coupled in a one-way coupled fashion. What it does is in ELM, in the land model, the irrigation scheme will evaluate the irrigation demand based on the soil moisture at each time step, and it will separate this soil moisture based demand into two parts. One is sourced to groundwater, one is sourced to surface water based on a fixed fraction. For example, 20% from the groundwater and 80% from surface water, and this fraction is fixed. And then the surface water and groundwater demand will be applied to the cropland by assuming the water is freely available, meaning the demand can always be met. When it couples with the MOSART WM, the land water WM can use that information to inform the irrigation water extraction, as I said before, in the MOSART water management model. The biggest limitation of this scheme is that it doesn't consider the surface water constraint for the irrigation. The surface water constraint means that sometimes you don't have enough surface water for you to irrigate. In that case, you may, if you're using this scheme, you may overestimate your surface water. You may overestimate your surface water withdrawal, but underestimate your groundwater pumping. And also, you do not have a feedback from the. You do not have this feedback from the river model to inform the land model that how much water is available in the channel or in the reservoir for you to withdraw. So in this new development, we modified this, improved this scheme by a two-way coupled irrigation scheme. So in this scheme, we now have a back flux, the water supply from the river model back to the land model to inform the actual irrigation supply, so that you will have the constraint from the surface water. The objectives of this study, we have two objectives for this study. One is to implement this two-way coupled irrigation and evaluate this scheme in a historical 30-year period simulation coupling scheme comparing to the one-way coupled scheme we used before, and see how that how that will change the hydrological processes and irrigation processes. And this work has already finished, and the paper will be submitted very soon, probably next week. So in this study, we have developed a number of simulations to compare. In these six simulations, we have a baseline simulation, which we call the ID is NAT, indicating natural condition. In this simulation, there's no management, no irrigation at all. So it's a natural condition. And we have two simulations, one-way coupled. So the ID is 1SO and 1SG. So 1 means one way, and S is surface water, and O is one-way surface water only. That means the water can only be provided by the surface water source. There's no groundwater pumping in this scenario. And this one is 1SG, means one surface water, one-way surface water and groundwater. So these two one-way simulation are assuming irrigation demand is always met as I just introduced. So there's no surface water constraint. The surface water and groundwater partitioning is based on a fixed fraction. Then we have three simulations, 2SO, 2SG, similar to the 1SO and 1SG. And then we have a third one called 2SGM, which is assuming that we have both water constraint from the surface water, but we water demand to always meet the irrigation demand. This is the domain of our simulation. It's a global domain, and the climate forcing for EIM is it's a 30-year climate forcing from 1975 to 2004 at SE30 grid resolution. And for the MOSART WM, it's a 0.5 degree resolution. And the pink dots here you see is the reservoir and dams simulated in the water management model. And the colors here shows you the percentage of the area equipped for the irrigation. First, before we do that sixth simulation, we calibrate the model. So what we calibrate is a single term to inform the target of the irrigation. Basically, is a term related to the soil moisture to tell the model when to start the irrigation and when to stop. So here we have the comparison between the upper panel is a result from 4 other simulations using one-way coupled simulation, but calibrate to the observations. And the lower one is our simulation after the calibration. So you can see that these are compared at the country level because these statistics are provided by the country or state in US or province in China and Canada. Here is a scatter plot showing you that. They're met. Then we're in a few water budget terms, and we find the difference between the 2SG and 2SGM comparing with the 1SG. So again, I want to remind you that the 2SG is the two-way coupled surface and groundwater. Surface water has constraint, but 1SG is surface and groundwater, but without constraint. And 2SGM is water always met, and surface water is constrained. As you can see, the first comparison is done for the total irrigation withdrawal. And the left one is the 2SG. So the blue means that the 2SG condition has less irrigation withdrawal because of the irrigation constraint. But the 2SGM, since the water is always met by pumping more groundwater, in some places you will see more irrigation withdrawal because you will have more water demand. In the model, the water demand is higher because of the heavy pumping of the groundwater. And if you look at the evapotranspiration comparison, you won't see much difference. But for 2SG, you will see a less evapotranspiration. It's reasonable because you are reducing the irrigation supply, so that you are reducing the evapotranspiration. But in the always met condition, 2SGM, it doesn't have too much difference. And then we are looking at the runoff, or we can call it return flow. It is the flow generated by the irrigation only. So as you can see that since we reduced the irrigation withdrawal, the 2SG has less return flow. The flow, the water applied to the grid cell, it's been most of the flow has been used to recharge the groundwater because of the pumping. Another thing we compared is to aggregate the global grid cell. We also look at the water table depletion rate. So as you can see here, we compared these 5 conditions. The top ones with stars are surface water only condition. So there's no water pumping. So the water table is always like it's a flat. But with 1 SG, meaning that you have a fraction of the groundwater pumping, fixed the fraction, it's about 20 millimeters within 30 years. But with 2 SG, but with two-way coupled scheme, 2 SG and 2 SGM, we will get about 2 millimeter per year, which is more closer to the GRACE estimate, which is 2.6. Although the GRACE estimation is started after our evaluation, but since we considered that more irrigation is needed in the future, after year 2000, so probably we will see higher water table depletion rate in the GRACE observation period, actually. And then another aspect we were considering is that the irrigation allocation. So it is important because you wanted to know how much water has been extracted from surface and groundwater sources. With more pumping. So here we're looking at the spring condition. The red one means that the water is pumping from the surface water, and blue one means pumping from supplied from the groundwater. And in summer, it looks like this. But if you are looking at the difference, you will see some interesting findings that in one-way coupled, since the fraction is fixed, you don't see any difference between spring and summer. But with two-way coupled condition, you will see some difference. Some places, when the season is changed, you will pump more groundwater, but some places will use more surface waters. For example, in India, the monsoon season comes, so they stop pumping the groundwater as they usually do in spring. So yeah, so here the two-way coupled scheme is able to capture the seasonal dynamics of irrigation water allocations. Taking one basin as an example, we did a Mississippi comparison for these 3 scenarios, and we see that the two-way coupled actually better match with the USGS report statistics with the fraction of the surface and groundwater sources in terms of the irrigation withdrawal. So here I wanted to summarize some of the findings. In the paper, we have more figures and the results, but here I'm just highlighting a few of them. Comparing to the one-way scheme, the two-way coupled scheme with surface water constraint result in less surface water withdrawal and less return flow because you have the surface water better GRACE estimation, and the two-way coupled scheme is also able to capture the seasonal dynamics in terms of the water allocations. We also have some uncertainties and limitations in this study. Here I list a few. Representation of the irrigation application. So in this study, we assume that everywhere in the world they use the same method to irrigate, which is the dripping. But some places they're probably using flooding method to irrigate, or if you have rice paddy, you will flood the area and you will use more water. And so that will also affect the water demand estimation here, which is important in the model in the withdrawal estimation. And also the climate data has uncertainties. Here we are using NE30 resolution climate forcing, but actually we have better, we should have better choice for that. And the land use land cover is fixed over the 30 years period, which can be viewed from the comparison with the other model, which has a dynamic land cover change. Here in this figure, I'm comparing the US and India. US during the 30 years, it doesn't have a lot of irrigation, cropland development, but in India, it's getting increased. So our model cannot capture this trend, but in US, we're doing better job. Okay, so this is the first study. The second study, I want to use 3 slides to quickly introduce what's going on there. So it's an ongoing study related to the global flood inundation analysis. As I introduced before, or we have this only sub-catchment. This one is based on the grid resolution. It's also 0.5 degree global, and we evaluate these many basins here, and we categorize these basins by the level of human impacts. So as you can see, in some basins, it doesn't have human impact, but some are heavy and moderate affected. Here are some results for the model. So as you can see, Amazon is categorized as a moderated affected basin, and satellite-based observation comparing with simulation. And this third column is the flow discharge, river discharge at the outlet of the basin. And the comparison pretty good. But Mississippi Basin, you see we are doing not that good job, because in this simulation, we do not consider the water management conditions. So as I mentioned here, our next step is to develop a model scheme that can couple ELM, MOSART, WM, and inundation components together. For now, since the model is since the water management model and inundation components are developed separately, they don't talk to each other for now, but in the future, we will make them talk to each other. And some quick preliminary findings here. We wanted to actually look at the generating mechanisms of these floods in these basins. We are taking Columbia River Basin as an example. So here, different color shows you that shows you the different generating mechanisms. So as you can limited flood, except for the downstream area, which is dominated by the rainfall and antecedent soil moisture. What we were trying to do is to look at the controlling factor, the role of the controlling factor in the historical period. So we find that the snowmelt controlling factor is actually decreasing over the 50 years in our simulation. So this is some preliminary findings. We're still doing our explore the way we do the analysis. So finally, I wanted to go through some ongoing developments. So here I'm listing 3 of them. It's all based on also based on the MOSART platform. For now, Hongyi has already developed a river temperature model, which can represent the heat transport in MOSART, and reservoir stratification, which is this paper also from his team, to support the BGC simulation. Can simulate in the future. It can also simulate the carbon and phosphorus and so forth. And also, Hongyi's team and Zeli has developed a sediment transport scheme in MOSART. Zeli has improved the ELM to capture the hill slope erosion, soil erosion, and Hongyi combined these two and to let the sediment transport through the river channel. And as I mentioned before, we wanted to make the water management and inundation components talk to each other, and this is an ongoing development. Well, which of them will heavily change the water budget in the water cycle. It also will impact the land-atmosphere interactions. So it's going to be interesting to see how the irrigation impact these interactions using the coupled E3SM. And also, so currently we were using a simple soil water model in the ELM, but Gautam has developed a variable saturated flow model. If we use that model, I believe we can better capture the soil water process in the irrigation process. I talked to Eileen the other day, and she actually did some sensitivity analysis about this VSFM. She find that with this, you will see a wetter soil, which means you probably will have less water demand in your irrigation, which is important in the which is an important information in irrigation water demand estimation. And also, we want to couple the E3SM with the GChem because for now the irrigation, the water demand is only provided by the irrigation, but GChem can support to provide the water demand from other sectors. And another issue we want, for the future direction is to using the same grid in ELM MOSART. It's been discussed for a while, and we have proposed this topic in all hands meeting next month. So the idea is that, so for now, the ELM is using a spectral element grid, which is different. We discussed the possibility to use the same grid to reduce the uncertainties between the coupling. And also for the floodplain inundation, we wanted to do some sensitivity analysis because for now it's when we developed this elevation profile to separate the channel and the floodplain, we just use 10 different segments across this grid cell. But in the future, we want to discuss the sensitivity about how to generate the evaluation profile. How does the floodplain inundation sensitive to the grid resolution and the vegetation conditions with and without trees and so forth, something like that. So, okay, I think my time is up. So thank you very much, and I'm waiting for some questions.
Great, thank you, Tian. And I'm going to stop the recording in a moment, but just so everyone knows, the slides are on Confluence and will be published on e3SM.org together with the recording.